Neil Lane is a senior fellow in science and technology policy at the Baker Institute and also the Malcolm Gillis University Professor Emeritus in physics and astronomy. He also previously served as assistant to the president for science and technology at the White House in the Office of Science and Technology from 1998 to 2001. So I'll go ahead and hand over the mic to Neil Lane, and he'll introduce the speakers.
Well, good morning, everyone. I had home duties yesterday, so I was not able to attend, but I did watch the webcast, which worked really quite well. But it reminds me to remind you to use those mics when the question time comes up, because otherwise it's very hard to hear. Now, one of the reasons it's hard to hear has to do with bioelectronics in my case. I have hearing aids. Thank you very much for whoever invented those. A pacemaker. What are my other connections? Well, I'm an octogenarian, so down the road I've got other organs and body parts that are going to need some attention. So any of you that have got any really great ideas, I just want to encourage you. Quite seriously, it was a wonderful session yesterday. I learned a lot. I didn't know much about this field, and I still don't, but I am impressed with the progress that's been made, being made, and also how incredibly difficult this really is. So I congratulate all of you working in the field and for all you have done. The only other, maybe it's a connection with bioelectronics. When I was working with President Clinton, I was pushing the nanotechnology, National Nanotechnology Initiative. And I remember testifying, probably was on the House side, on behalf of the President's budget for fiscal year 2001, in which we had $500 million for nanoscale science and engineering research in the various agencies. And as I talked about the wonders of nanotechnology, spinning it as best I could, it's going to revolutionize all other technologies, computing, certainly materials, medicine. You have all these non-invasive things running through the body. You're not even going to notice them. They're going to cure all illness and take care of all disabilities and so forth. One congressman in particular looked kind of interested, which struck me as odd because never seen a congressman look interested in my testimony. And so when question time came, he made clear, I've forgotten exactly what he said, but let me put it this way, that he'd recently had a lower GI examination of some kind. And he said, "This is great. Next time I do that, I'm going to tell my doctor I want one of those nano things." So that's as close as I come, and I don't know if we're quite ready for those nano things to do that particular job, but they do other things. And extraordinary thing that I was particularly interested in is how, not just then, but what we've learned since then, how much the properties of materials really do change at the nanoscale and maybe larger scale. And we heard something about that yesterday, I guess, the solubility of silicon in water, for example, which I never really thought about. So the challenge, though, of course, is at the nano-meta interface, rather like the challenges, I guess, some of them that we'll hear about today between the level of a microbial life and cells in larger animals and so forth, like humans. Anyway, this is a exciting session. Some of the things we'll hear about today is bacteria, the good ones, I think. Maybe we'll hear about some bad ones, but they're all around and inside and outside. And it's quite extraordinary research that is going on. So we'll start out with Jason Robert, our first talk of the morning. He is director of the Lincoln Center of Applied Ethics and Dean's Distinguished Professor in the Life Sciences at Arizona State University. He is going to watch after my grandson, who's a freshman at Arizona State University, who's proudly swimming for the university. And his grandfather hopes he's also doing something on the academic side, but so far I have yet to learn about that. So please welcome Jason to his talk.
I want to apologize first off. You all heard way too much from me yesterday. I couldn't help but jump up and use that microphone over and over again. But I'm kind of the guy who doesn't fit in as well in this panel this morning, but I think the reason I was put in this session is to kind of bridge yesterday and today. So I'm going to do a little bit of that work. And I'm going to tell you a little bit about me. I'm a kind of stranger in a strange place most of the time. I'm a Canadian who lives in Arizona, so all by itself, that's some kind of indication of how I don't always fit in. At the same time, at this meeting, I feel I fit in really incredibly well, not least because Raphael and his colleagues have done such a great job of bringing more than one philosopher ethicist type to the meeting and involving us in the panels so that we don't feel that we're just tacked on at the end as a kind of afterthought, but rather integrated more fully into the discussions. And that's terrific for us, and I think the team, Raphael, Kirsten, and others are to be commended for that. Another way in which I fit in is I went to Wilder Penfield Elementary School in Montreal. We heard about Wilder Penfield yesterday very briefly in one of the presentations. So I'm a philosopher of biology and ethicist, but I'm tenured in the School of Life Sciences at ASU, and that's a choice I made. I don't actually have an affiliation with the Department of Philosophy, and I used to teach in a philosophy department, and they said to me things like, "You're very clever, Jason, but whatever it is you do, it's not philosophy." And so you'll hear things from me today that will make you understand that, I imagine. Not maybe the "you're very clever" part, but the "whatever it is you do, it's not philosophy" part will make perfect sense. I am a longtime collaborator of neuroscientist in the bioengineering department at ASU who works with non-human primates. And in fact, I spent some time with him over the course of the last decade doing some of the hands-on work. And my attitude toward this was, it's important to have credibility in the field, and it's important to have credibility with the scientists, and in particular, in this case, with his students. It's one thing to be an ethicist embedded in a science group and sort of, have a chance to interview the students and talk to them and interview the PI and the lab tech and so on. But sometimes there's just a sort of hint of suspicion, what the hell are you doing here? What do you have to offer? And so forth. And my attitude was, I didn't want to feel to them that I was some outsider or an interloper. And I certainly didn't want them to think that I was there on behalf of, say, the people for the ethical treatment of animals. It's already the case that any kind of experimental intervention with a non-human primate is ethically challenging. This is work that is very, very tightly constrained ethically and in terms of governance. This is work that is very, very carefully scrutinized at all levels. The lab that I've spent time working in is one of the only ones at ASU that has not been subjected to a Freedom of Information Act inquiry for the medical records by PETA. And there's a reason for that, I think, and it's that the PI has taken very seriously the idea that this is important and very difficult work that needs to be done especially well. And the reason that we started working together is pretty straightforward. So his name is Steve Helms-Tillery. He used to collaborate with Andy Schwartz. We heard about Andy yesterday in the presentation. I'll talk a little bit about it as well today, about Jan Schurman, who was the recipient of the Utah electrode array, the double implantation. She's the one who has Lewis and Clark implanted in her skull. And Andy used to be at ASU once upon a time, and Steve and Andy collaborated together on that work. And Steve had witnessed some, I would call it, and he did too, abuse of non-human primates in one of the labs and at ASU. And so he developed a protocol for training the students in the proper conduct with non-human primates. And he brought me in early on in this process to help work with some of the students. And so I spent time actually training with the students and training with the monkeys in order to be able to develop some credibility with the students as well, and so was involved in a project. It was what I will call later today a non-invasive protocol, in as much as the intervention that they were testing was basically an ultrasound. So not to be flip about it, waving a wand at the monkey to assess whether the intervention was successful. And yet the initial intervention was to create a hemi-Parkinsonian monkey, which meant that the monkey was treated, that's what they say, treated with MPTP, so a chemical lesioning of one side of the monkey's brain, so that the monkey developed motor symptoms that mimic the motor symptoms that we see in Parkinson's patients. And so the hemi-Parkinsonian, this was a vervet monkey, African green monkey. The vervet developed these symptoms, and then we waved the wand at the monkey to see if it got any better. And so I was involved in this protocol, and then was also involved in the termination of one of the monkeys, so the vivisection euthanasia of one of the rhesus macaques involved in another study. And this allowed me to develop some credibility with that research team, and allowed for a real breakthrough with one of the PhD students who was really not at all interested in talking to me until after I was there holding the hand of the monkey as the monkey was put down. And then she opened wide up to me and was willing to talk to me about some of the challenges in working with this particular population of research subjects. And then this is the only disclosure I have, I guess, which is that I'm working with Steve. I'm currently funded by DARPA, the Defense Advanced Research Projects Agency. We work on a project called Transdermal Electrical Neurostimulation for Performance Optimization, or TENPO. This is a part of a program called TNT, which I'll talk about a little bit later. It was initiated by Doug. I don't know if Doug is here today. Doug Weber was the program manager for that. It's now being led by Tristan McClure-Begley at DARPA. And so I'd love to have other disclosures, so if anybody wants to hire me, just let me know. Now, we heard a little bit yesterday about some of the early work with invasive neuroprosthetics. So this is from an article in Scientific American in 2002 by two of the more showboating folks involved in neuroprosthetics research, Miguel Nicolelis and John Chapin. And the sort of call-out text says, people with nerve or limb injuries may one day be able to command wheelchairs, prosthetics, and even paralyzed arms and legs by thinking them through the motions. And the image posted here from that article in Scientific American is of an owl monkey named Bell, who was able to control this robotic arm over a significant distance. The arm was located at MIT, and Bell was at Duke, and Bell was able eventually to be trained to control that robotic arm with her thoughts, and the thoughts were sent over the internet. That's not particularly interesting, right? I mean, the thoughts could have been transmitted just into the next room, and it would have been just as compelling, right? The fact that it was sent over the internet isn't all that interesting, but nonetheless, it led to some big headlines. That was 2002. For what it's worth, not a whole lot has happened since then in terms of turning this into clinical realities. But what's fascinating about this is the whole idea behind this field was kind of established around this time as well, though there'd been maybe 50 years of foundational work that was in place. This is summarized by John Donahue, again in 2002, in this figure. The idea is that we want to have these output and input brain-machine interfaces. We want to be able both to have an output device, that is, we want to be able to read or measure and analyze the electrical activity in the brain, the popping sounds that we heard about yesterday of the electrical firing in the brain. And we want as well to be able to stimulate some aspect of the brain, and that stimulation may actually turn out to be the enabling of new percepts. For instance, in the case of the visual cortical prostheses that we heard about yesterday. And in a paper I published almost a decade ago now, and this ties into what Neil said earlier about nanoscale science and engineering, because ASU was one of the places that had a Center for Nanotechnology and Society in which I was involved. I argued that one of the fundamental technological challenges in neuroprosthetics design that nanoscale science and engineering might be able one day to help solve is the development of small, physically non-invasive, flexible, reliable, chronic, multi-electrode recording and signaling methods for the cerebral neocortex and other parts of the brain. So this is a technical challenge that has not yet been resolved, although we're making some progress. Now, in that 2002 article in Scientific American, there was this kind of elementary image on the right-hand side that was put forward. I call it an ancient dream because, let's face it, that looks positively archaic according to our standards today. Look, for instance, at that backpack computer. That is an outrageously, on the one hand, futuristic design, and on the other hand, archaic design, right? The phone that I have in my pocket right now is a gazillion times more advanced than, and I only have an iPhone 7, right? But a gazillion times more advanced than the backpack computer that is depicted in this futuristic image from 2002. But the idea here is that you've got somebody with a spinal cord injury who is using a wheelchair and who has an implant. In this case, this is probably going to be, probably the imagination was some version of the Utah microwire array implanted in the motor cortex, and the microwire array is going to, this is futuristic still, send wireless signals to the backpack computer, which is then going to run some algorithms which are going to allow for a muscle control chip and some other kinds of electronic devices in the wheelchair, allow for the individual to move the wheelchair around, to move the arm, and to be able to move forward. And just to give you an indication, we saw this yesterday. This is the Utah array here, and to give you an indication of scale, this is it on a penny. So it's a tiny little device. I think we'll hear more later about, so this is a 10 by 10 microwire array. We'll hear later about significantly more exciting and elaborate kinds of microwire arrays that are currently under development, and hopefully we'll see some new stuff in the relatively near future. But this remains the kind of thing that most folks in implantable neuroprosthetics using a microwire array are still working with today. And again, this is a figure from 2002. So this image from 2002, this ancient dream, came to fruition. And again, this is an image that Aaron put up yesterday for us. This is what was thought of as one of the first real serious clinical breakthroughs. This is in 2007. Matthew Nagel was one of the first recipients of a microwire array implanted in his brain. So Matt Nagel, just to give you the background on this, in 2001, he experienced a spinal cord injury as a result of an altercation at an Independence Day event. He was paralyzed but maintained the function of speech. And he was implanted with this device. And so again, you see, for scale, the microwire array on a penny. You see that it's attached by microwires to this sort of pedestal that is going to be implanted in his skull. You see where it's going to be placed in his brain. Then you see, so you don't actually see the pedestal, you see the cable that's connected to that pedestal. That cable runs not to a backpack computer, but rather to a larger computer in the clinical setting. And what Matt is able to do as a result of this device is move a cursor on a screen. And the way he puts it, I can't put it into words, it's just I use my brain. I just thought it. I said, cursor, go up to the top right, and it did. And now I can control it all over the screen. It will give me a sense of independence. So while he can talk, now he has the capacity as well to communicate with the outside world via a sort of physical independence, because he can control an electronic device, a machine, with his thoughts. And for those of you interested in learning more about these kinds of things, I should point out, just in the the realm of serendipity, that last week's issue of the New Yorker had a long article detailing the most recent activities of Jan Sherman, Andy Schwartz's patient, in the article is called "Degrees of Freedom, a Scientist's Work Linking Minds and Machines Helps a Paralyzed Woman Escape Her Body." So I have a copy of it, but you can all just get it on the New Yorker website, or you can download it. It'll take you an hour and 24 minutes and 54 seconds to listen to it with the Autumn iPhone app. So there's a kind of brain machine interface if you want to do that. It might even still be on the newsstands if you want to read it yourself. There's a little discussion in there, the Matt Nagel story as well. And there's, of course, Jan. We didn't hear yesterday about what Jan most wanted out of the surgery when Jan volunteered to have Lewis and Clark implanted, and she was going to use a prosthetic arm that she eventually called Hector. What she most wanted to do was feed herself chocolate, and that's what she managed eventually to do. And we didn't hear yesterday about this, but it's one thing I thought would be worthwhile pointing out. We heard about visual cortical prostheses, but we didn't hear about speech prostheses. This is an interesting area. Has anybody heard of Phil Kennedy and the work that he's done in this space? A couple of you have. I met Phil a number of years ago. He came out to visit us at ASU. Phil's a fascinating dude. This is an article in Wired a couple of years ago detailing his most recent efforts here. Phil Kennedy is an MD based in Atlanta, and he had developed in the 90s and got some NIH provisional permission to implant these handmade electrodes, these glass cones, into which human brain tissue would grow. And these would be implanted, so the sciatic nerve in particular would grow. He would implant these into the brain of patients who had locked-in syndrome. So locked-in syndrome, very debilitating. These are folks who are fully conscious and aware, but have zero ability to communicate with the outside world. Beautiful film and book about this. In English, it's called The Diving Bell and the Butterfly. Jean-Paul Bauby describes his experience with this, and he dictated his experience with locked-in syndrome with the only capacity he had to do that was he had the ability to control one eyelid, so he typed out the manuscript of The Diving Bell and the Butterfly with his eyelid. And it was turned into a film. Incredibly powerful stuff, totally worth reading and or watching. So Phil Kennedy thought, well, what if we could find a way to enable folks who have locked-in syndrome to speak? He implanted a couple of patients. One of them, Johnny Ray, seemed to be doing fairly well. It didn't end up working out too well. Johnny Ray eventually passed away in 2002. A couple of other patients did not have much success. Over the next couple of years, Phil Kennedy lost NIH approval to continue with the surgeries because the safety and efficacy had not been demonstrated under the time that he had NIH approval. He lost his grants, he lost his funding, he didn't quite know what to do. In 2014, he decided, well, hell, I'll just go ahead and do it myself. So he found a surgeon in Belize who would be willing to go ahead and do the surgery on him. So he packed up his supplies and went down to Belize and had the glass neurotrophic electrodes, as he called them, implanted in his brain. Did not look good for a couple of days. They were concerned that they broke him, but it turned out he, once the edema and various other post-surgical effects wore off, he was okay, went back to Atlanta, started seeing patients again, then went back down to Belize and had another surgery to have the very elaborate electronic devices. He doesn't know about microelectronics. That was the joke in the Wired article. So he has the more elaborate, larger devices implanted in his skull and manages to get some interesting data out of this. Then there are some complications. He's able to have the surgery, to have those removed in Atlanta. His insurance will cover it because it's a life-saving surgery at this point, just to have those removed. He doesn't bother having the neurotrophic electrodes removed because they're already sort of functionally integrated into his brain and so forth. So, and now he seems to be fully recovered, at least on the one side of his brain. He's not sure whether he'll go back and have the other side implanted, but he might someday. But, you know, pretty fascinating stuff. This is the kind of thing that's happening on one of the kinds of things that's happening on that side. Now, the ancient dreams, I think, I'm going to make a strong claim here, are under-realized. The patient outcomes have generally been quite poor, at least for these kinds of things. I'm not talking about deep brain stimulation at this particular moment. For deep brain stimulation, the patient outcomes have been pretty darn good, with the exception of the hypomanias and so forth that I mentioned in my question yesterday. There has been some corporate and investor attrition, at least with some of the devices and some of the approaches. There's certainly been very slow progress compared to initial promise and the promises that were made on behalf of these technologies. Everything I've said so far is about stuff that happened mostly in 2002, and virtually nothing has gotten better since then, especially with regard to patient populations. And there seems to be some disarray in the field of implantable neuroprosthetics. Now, the Biological Technologies Office at DARPA, nonetheless, is really persisting, right? They had this really interesting prosthetics program in place for a number of years. Biological Technologies Office gets reorganized or gets established a few years ago. They've really started to push, despite still having a strong program in implantable neuroprosthetics, they've really started to push most recently into non-implantable modes of neurostimulation, neuromodulation. And the two programs that I'm going to mention really quickly, one is targeted neuroplasticity training, which I mentioned already, TNT, and the other is next generation non-surgical neurotechnology, or N-cubed. So TNT, the idea is to use a neurostimulation device activating peripheral nerves to boost synaptic plasticity. And Tristan McClure-Begley, the program manager, describes this as basically an educational platform. What he wants to do is really use targeted neuroplasticity training to enhance, to sort of piggyback on neuronal plasticity to enhance cognitive learning. Fascinating stuff. There is a little bit of implantation stuff, especially if we're talking about vagus nerve, because vagal nerve stimulators tend to be implanted, as we heard a little bit about yesterday. But some of the other work, trigeminal nerve stimulation, for instance, and other kinds of stimulation is non-surgical. And then next generation non-surgical neurotechnology, which is launched this past year by Alamondi, a new program manager at DARPA, has as its strong ambition to go for high-performance bidirectional brain-machine interfaces which are non-surgical, which don't require any surgical implantation. And some examples of non-surgical neurostim are things like microprocessor-controlled light and sound systems, transcranial magnetic stimulation, which has been around for quite a while, and then various forms of transcranial electrical stimulation. So the light and sound system stuff has been around for quite a while. This is one example of the commercially available stuff from MindPlace. Totally worthwhile to explore, especially if you're stuck for a Christmas present. By the way, if you're also stuck for a Christmas present but you want to spend a lot less money, I highly recommend, since we talked about Frankenstein yesterday, this is a shameful plug because I'm Canadian, so it's very shameful, but I did edit with 2 colleagues a new edition of Mary Shelley's Frankenstein for the 200th anniversary. It's annotated for scientists, engineers, and creators of all kinds. MIT Press published it, available on Amazon for under 20 bucks. Very well reviewed, beautiful edition, highly, highly, highly sought after as a stocking stuffer, so definitely buy it. But if you want to spend 300 bucks, you can go ahead and pick up one of these devices. I have the Proteus, which is the cheap one, and it really is cheap. But the idea is that you put it on, close your eyes, sit in a quiet room, and it plays weird sort of psychedelic music and flashes a light show, and it'll calm you down or stimulate you, get you all hyped up without having to drink Monster, smoke cigarettes, or do coke. Transcranial magnetic stimulation is another of the forms of non-invasive, quote-unquote non-invasive, certainly non-surgical kinds of devices that are out there. We heard a little bit yesterday about electroconvulsive therapy. Very often people think of poor old Randall from One Flew Over the Cuckoo's Nest, but there are way more, way less dramatic forms of this. I was really grateful to Hank yesterday for telling the story about his family member who had undergone ECT for the treatment of depressive psychosis. And Mayo Clinic and various other, in this case, Medical University of South Carolina, from where I stole this picture, have been advocating the use of ECT for various kinds of psychiatric conditions. And even though it's typically used only for treatment refractory kinds of conditions, nonetheless, it seems under controlled circumstances and under anesthesia to be doing some good in the world out there. It still harkens back to a very dangerous time in psychiatry, but nonetheless, it could be a potentially useful form of non-surgical neurostimulation. Transcranial direct stimulation, we heard, direct current stimulation, we heard a little bit about yesterday. And on top of that, there's another sort of approach that's emerged in recent years, which is attempts to use trigeminal nerve stimulation, so electrical stimulation, the trigeminal nerve, which has all kinds of projections into the body that appears to have some usefulness for some neurological and neuropsychiatric conditions. And then, of course, there are all kinds of commercially available devices. This one has gotten a lot of play, the latest issue of Men's Health magazine, which, as you can tell from my physique, I read religiously. The Halo Sport and Training Package, totally worthwhile at only 425 bucks, and will be delivered in time for Christmas. Sworn by all kinds of professional athletes and other folks, uses peripheral nerve stimulation to enhance performance. Again, this focuses on plasticity. It's a plasticity intervention, or they call it hyperplasticity intervention. Now, I'm going to wrap up with just this one slide that is what I want you to focus on. The idea very often is that surgical neurostimulation is invasive because there's surgery required, and so it involves moderate to high risk. By contrast, non-surgical neurostimulation, because it's non-surgical, is putatively non-invasive, and therefore it's comparably low risk. And so one of the reasons that the military, through the Department of Defense, through DARPA, is interested in potentially non-surgical neurostimulation is just that. It's lower risk. But with surgical neurostimulation, you've got a relatively precise input-output situation. And with non-surgical neurostimulation, because you're blanketing the brain, and you're also, it's not clear exactly what you're targeting, you've got at least a presumption of a less precise input-output situation. You can control in various kinds of ways, as we heard yesterday, but there is definitely, almost by default, less precision. And you've got very narrow deployability with with surgical neurostimulation, because it requires neurosurgery. Typically, it requires an implanted device that's going to require follow-up. And there's very moderate therapeutic creep, although we've seen deep brain stimulation used for a wide range of conditions, not just Parkinson's disease, but depression, anorexia, obesity, and various other things. By contrast, non-surgical neurostimulation, you've got wide deployability and extensive mission creep. By that I mean everybody's using it. The Halo device available widely is one example of that. Now with surgical neurostimulation, you still end up with the moderate to high risk profile, but because of these considerations with non-surgical neurostimulation, I think we have to erase the idea that this is a low risk enterprise and consider the possibility that it's moderate to high risk. And what I worry about is that there are some trade-offs at the surgical, non-surgical juncture, and this idea that surgical is invasive and non-surgical is non-invasive, that distinction, which is doing a lot of work, is doing some dangerous work. It's eliding the non-surgical risk. It's promoting a false sense of security. It's distracting us from other issues. And it's potentially evading some governance structures. So just to wrap up, I think there are some additional issues to consider: the adjunctive and interactive effects of devices and drugs, the unintended consequences of intended uses, and for what it's worth, a lot of the innovation that's happening with non-surgical neurostimulation is happening in the do-it-yourself community via daisy chaining and kludging of neuromodulation devices and strategies. We heard about the now defunct Radio Shack yesterday from Hank, but you can get these things all over the place, and the iontophoresis devices can be easily built, daisy chained together, and potentially have very serious effects. And on top of that, there's the possibility for widespread deployment over the counter and off-label without any oversight, and usually without any mechanistic understanding of why it works and what goes wrong when it doesn't. And that suggests to me that we need to have a very serious conversation about the risks, benefits, uses, misuses, and abuses of not just the surgical neurostimulation modalities, but also the non-surgical ones as well. Thanks.
Speaking as someone who also has a lot of DARPA funding, what kind of, I don't want to use the word push, whatever, perceptions do you get from your colleagues and friends about DARPA funding of this kind of work?
So it's really interesting. So there are two kinds of things. So I'm going to talk about the within DARPA and then the beyond DARPA. So the within DARPA thing is fascinating. So when DARPA made the call for the TNT proposals, they actually requested ethics integration. And my understanding is that of all the proposals that went through to TNT, only the ASU proposal included an ethics component. Now, DARPA has its own ethics committee, but we were the only one that included it. And when we went to the launch of the TNT, when we were funded, we went to the launch of the TNT, Doug Weber said, "Wow, this stuff is so cool. We want you to be the front-facing aspect of ethics for the entire TNT program, not just TENPO, yours, but everything. And by the way, we're not going to give you any more money to do that." So of a $6 million budget, I think, for the TENPO program, we cost $80,000, and we're doing it for all 11 projects or whatever. But that's fine, because I'm cheap, and it's easy stuff. So on the one hand, I take that as a good sign that DARPA is actually interested, and DARPA, when we did our initial workshop at the ASU DC Center, Justin Sanchez, who's the BTO director, actually came to the workshop. And so DARPA's had some buy-in. That makes it easier to talk to my friends and colleagues outside of DARPA about having DARPA money. So I really do think that DARPA's got an interest in this. They didn't really want us to talk, DARPA didn't really want us to talk a whole lot about performance optimization and enhancement of warfighters and all that other stuff, because their push has really been making the returning warfighter whole rather than enhancing the capacity for warfighting. I'm not sure that I totally buy that, but nonetheless, that's been one of our take-homes. At the same time, I do have a lot of colleagues who aren't thrilled with the fact that there's a sort of militaristic aspect behind this work. My attitude is the folks that I've been working with very closely are definitely focused on patients and on improving the lives of people who are suffering from various kinds of physiological and psychological challenges. So my emphasis has just been on trying very hard to work within that space and worry less about where the money's coming from. So maybe it's a hiding my head in the sand kind of response, but I'm okay with that. It's $80,000.
Oh, well, chump change for defense.
Yes,
Right?
chump change for the defense budget.
Thank you for a wonderful and all too brief talk. I am currently overwhelmed by multiple data streams. How do I shield myself from bad code?
So two things. One, hide your head in the sand. No, to be honest, one of the things that I did earlier this year, I went through a pretty severe depression and actually needed a little hospitalization and some serious retooling of my coping skills earlier this year. And one of the things I did is I stopped reading the news for a while. I stopped listening to the news online. I don't mean I shut myself out from it, but I got a subscription to a physical newspaper. And I started reading the New York Times when I wanted to read it, rather than getting it sort of pushed to me all the time. So for me, slowing down was one of the things. And so also I write with a fountain pen and little things like that. I don't always get my email pushed to me, things like that. So just a little bit of sort of owning my environment and sort of protecting myself. That's one of the things I've done. The other thing is, well, I don't know if it's a coping strategy. Is sort of constant vigilance, right? I mean, so surrounding myself with people that I trust and people that can sort of help me keep track of where I am. I kind of think of it as a kind of social proprioception, right? Or a social kinesthetic awareness or something like that, sort of tracking where I am and how well I'm doing. And so when somebody says to me, look, Jason, I've known you for 10 years, you've been depressed the whole time I've known you, but now you're really dysfunctional, that kind of thing is really helpful to me. And so surrounding myself with people that I can trust to be able to tell me things like that has been really useful. Now, I mean, I hope it never gets to that for you, although you're a psychiatrist, so it probably does. But that kind of thing has been really useful. So part of it is just managing my own space, and then part of it is just making sure that I've got kind of a shield of protectors.
One more question.
So, Jason, I've been interested in the do-it-yourself side of this and the OTC side, particularly with transcranial direct current stimulation. My impression is that wave may have crested, but I'm not entirely sure. Do you have any thoughts about whether there is a plausible way to try to regulate do-it-yourself use of TDCS, and if so, whether it's worth it?
Yeah, so I don't think that there is a plausible way to regulate DIYs. There was an article a couple years ago, Journal of Law and Medicine by Marone Bixen and colleagues that cited some of the law review and other literature on attempts that have been made so far. Their suggestion was the key thing that we can do is make sure that we hold device manufacturers to the highest standards with regard to their own devices. And so make sure that just because DIY stuff is happening, we don't want to let standards slip for device manufacturers and so forth. And that might make it the case that we protect consumers within the sort of normal chain of things, as well as from complications. And that also might make, the idea is to try to make these devices harder and harder to hack, as it were, within the DIY community. Beyond that, I don't know that there's any sort of serious prospect of regulating that.
Thanks.
Thank you. Please thank
Thanks, Lee.